All right, everybody, welcome back. So this is the last section for Tidyverse. So in this section, we are going to learn some method to iterate over list, and also we are going to learn some method that help tidy up the model objects. And in the end, we want to combine those methods that we learn to construct a consistent workflow for data wrangling and statistical modeling in the Tidyverse. So that will be the three goals here. And we'll use the same the twin data set. And here for this section, we have two tasks. Number one, we want to do the model-based summary of feature intensity for all proteins in every run. So previously, we do the protein level, we do the summarization based on log of sum, that kind of operation. And in this section, so we want to model the log intensity of feature for each protein with the LM function. Essentially, we want to consider the effect of the feature and the run, and we treat them as a fixed effect. And we want to obtain the run level summarization with the fit model. And after that, and in text 2, we're going to perform the hypothesis testing to find differentially abundant proteins. And so in this section, we'll discuss essentially the tool to perform the modeling and testing based on two approaches. So the first approach will be we'll just make use of the for loop method. We'll just take the for loop and to loop over here, for example, the protein and the run to make the summary. And also, we'll also learn how to make use of the list column that we discussed in the end of the last section, and how we can operate on those list columns. All right, so going back to my R console. And the first thing I'll do, I'll normalize the data, and based on the same approach to equalize the median of log intensity in the heavy channel for every run. And so the normalized data set restored in the twin DIA2. So here we have some additional column that is essentially we use those columns to do the normalization. So for the text one, so we want to summarize feature intensity per protein with a linear model. So here we treat the run and the feature as the fixed effect. So for those of you who may not be very familiar with the linear regression modeling, so here's roughly the idea. So if you look at the profile plot here, so across different runs, so you may see some shift in terms of their intensity across run. And also for different feature that show in different color, you can also see some different feature. They are actually at different level of the intensity. So for example, for list blue one, it's actually higher than this yellow one. So in the linear model here, we essentially try to characterize the effect for different run and the feature. And then in the end, after we fit this model, we extract those summary related to the run as the run level summarization to represent the summarization of feature intensity for that particular one. So again, here we'll just start with the subset of the data set. So let's just look at a subset where we have one protein and the 3 rungs here. And I will fit the LM model here. Now let's first take a look at the summary of what we fit here. And I forget to mention here, when I provide the formula here, I added 0 here, essentially to inform the function that I don't want to have the intercept as the coefficient here. So that in the end, those coefficients I get here, I will get essentially the full set of the rung effect here. And if we look at the profile plot here, for this one, let's take a look what this means. So you see in rung 1, so essentially it's saying the intensity for rung 1 it's about 16.8 and 16.3 for rung 2, 16.99 for rung 3, and that's the intensity for the first level of the feature. So here we have 4 features here. The fragments are Y5, Y6, Y7 for 2 charge state here. So the number we are looking at here is essentially the log of feature intensity for this one, for rung 1, for the first feature will be this one, the red one, and similarly for the second one and the third one. And what do those 3 rows mean? So this one essentially means compared to the first feature, the Wi-Fi here, the second one is lower than the first one, the Y6 here. So the Y6 is lower than the Wi-Fi by 3.4. And similarly, the Y7 with charge 1 here is slightly less than the first feature here by 0.05. And similarly for the last feature. And we look at the summary before when we look at the structure of the summary function, and so there are a bunch of different types of the summarization. And in order to extract the fit parameter for this model, we can use this coef function that would return a named factor for all the parameters here in this function. And if you want to get some more detailed information, so you can first code the summary function and then pass on the output to the coef function, and then essentially you'll get this matrix that shows in every row that shows the information related to the rung effect at the first level, with the point estimate and also standard error p-value and the p-value here. So now if we want to use this summary to perform rung level summarization, so one way we can do is for rung 1, we'll say this one will be the one that we want to, this value would be how we summarize the log of protein intensity for this rung, and similarly for the second and the third rung. So essentially, we'll use this coef function to extract to extract loads of fit parameter, and then we can create a table by first thing we want to have two columns in this table. The first column would indicate what type of effect, and the second one would show the estimate for that effect. And since we are only interested in the wrong effect, so we'll make a filter instead. And here we'll just filter for those rows where in their effect names that contains the wrong here in the value here, and that would essentially to exclude all those rows without a wrong here. And to further change the value for the effect, so we can use the stir replace, essentially to replace the wrong here by nothing here. So essentially that would remove the wrong here. So that's a way that we can extract the information from the fit model and then to derive the wrong level summarization for this small data set. And we can essentially use the same approach for the trained DIA data set that we are discussing. Right, now we want to do the summarization for all proteins. So we now have a way to do the summarization for one protein. So we can essentially loop over all the protein, and then for each subset, then we will just do the same thing that we just described. So the approach one for task one here, so we'll first to loop over all the proteins, and for each protein we'll fit a linear model here, and then extract those estimated parameters with coefficient and combine the result and with the result from the previous iteration using R-bind here. So let me just run this chunk of code. So essentially, the first line here, I'll get a unique set of the protein name. So in this data set, we have 33 proteins. And then we'll loop over each of the proteins. And for each of them, so we'll take a subset corresponding to each of the proteins. There's one protein here. Say, for example, this one, that take it from the last iteration. So the data frame one protein here will correspond to, the small subset correspond to one single protein. And we are doing the same thing. So we fit the LM model and we treat the wrong and the feature as fixed effect, and extract the coefficient by the coefficient and arrange the result in the table, and then filter out those unrelated rows, and then use R-bind to combine all the result for the result for all the proteins. So the result would look something like this. So we'll have a data frame on the table with the 3 columns, with the column for protein, the column for the effect that essentially is indicator for the run ID, and also the summarized value for that particular run for that proteins. So is there any questions so far about fitting a model, extract the parameter, and combine the result for all the proteins? So that's good. Yeah, so clearly this method can work, and as long as we know the unique set of protein that we are looking for, and we make a subset, and then we can work on the small pieces and combine the result. But it's usually not recommended because, first of all, it's not very efficient. And here, in every iteration, as you will see in the very end here, we do an R-bind here. That would essentially to make a copy of all the results from the previous iteration. So in every iteration, you are going to make a copy again and again. So that's not very efficient. And a better way to do that would be with a similar approach. However, in the very beginning, we create a list with the same length of the number of proteins. And then in the for loop, we'll do the same thing here, but we'll save the result, we'll save the table here in every element of the list. And in the end, we'll just use the bind row function from dplyr, dplyr, and to essentially to bind everything together into a data frame. So this approach would be more efficient than the previous one. However, both approaches discussed so far, they have two obvious drawbacks. The first one, again, we discussed this once and once again. So the output object of the modeling, they are not tidy. So essentially, we need to do some additional work in order to extract and reformat the summary. So what I mean is here, so in every step, we need to create this table essentially to extract the fit coefficient, and also, to provide what those value means. And so here, essentially, we need to make some additional effort in order to extract and format the result. And if we are now fitting with a different model, then we may need to use a different way, or at least to format in a slightly different way. And the second drawback here is every time when we fit a model here. So for example, here, in every iteration, we fit a model here. And once we extract the result, and in the next iteration, so we never save the result of the fit model for every iteration. And if at some point we want to, we think we may want to extract some other information from the model, then we'll need to run through the process again, because we did not save all the model for all proteins. And it would be good if we can construct or have a way to store our data and our model object in a somehow structurally informative way that we can get access to the grouping unit and the data and the model, etc. So I'm going to introduce some solution in the Tidyverse through the use of the first of all, I want to introduce some method to tidy up model object from the Bloom package. And then we'll talk about how to operate on the list column later on. So to be more specific, so why we need to worry about, the model object, and why it's hard to work with the model object. So again, I'll fit once again and show and print out the summary here. And for the fit parameter here, so this part will be the important. That's the parameter level summary we want to know from the fit model. And if we want to extract the information for this part, let's say to and also transform into a data frame format, then this is what you need to do. You need to first take a summary and then pass on to the COI function and to make it as a data frame here. And this is what we get. But this format is actually not perfect. Can anyone tell me what's wrong with this result in terms of formatting? Feature and run should be separate column. Well, for this case, feature and run, they are actually treated as an effect in this model. Yeah, so both of them they actually belong to an effect variable. Yeah, but they are actually placed here. So there's no column for run and feature here. So here they are restored as a row names. So if I save it here, and now you see it's a data frame with 6 observations and 4 variables. And those 4 variables, they are those 4 estimate standard error, t-value, and this guy.
The runs and features are saved as row names. The runs and features are saved as row names in this case.
Yeah. So yes. So they should be the value for a turn or for effect. However, in this format, it's restored in the row name here. So if I say row names for this one, so you'll see that's a row name for your data frame. So they are not actually placed in the correct place. Well, not in the convenient place that we want to work with.
You can create a column that contains row names as values.
Right. So, but yeah, we can do that, but we'll need to do that, right? So in the original format here, so there's something not well in the most convenient place that we want to work with. Yeah, we can definitely correct that, but we'll need some additional work. And the second thing is, what's this one? It's not really quite informative. So it's actually, when we print out the result here, so it's actually a column related to the p-value. But here, because it's the column then is not quite informative here. And when you convert it to the data frame, so you get something like this. So it's not very informative. And also, as I mentioned previously, there are also some information. For example, the p-value at the model at the model level summary here. So it got calculated due to when you call the summary function, but it's not restored. And also in this layout overall here, you actually have a mix of summary at different level. You have some summary for each individual measurement, so residual, and you have some information about the parameter of your model, and also you have the summary at the model level. So their degree of freedom, there's some statistic and p-value. So it would be nice. It would be nice if we can have a simple way to turn the model object and then to extract the meaningful information in a simple way. So that's why that's what the Bloom package can help. So Bloom is the package that turns the model object into data frame in the tidy format, and with 3 methods here. So the first one is called tidy. So what tidy does is to extract the parameter level summary, essentially this part. And that can be model coefficient and also statistic. In this case, it's t-statistic. And also another function called augment. So augment would extract the observation level summary for all the measurement we have, the predicted value, residual, etc. And there's also a function called glance. The glance would extract the model level summary that can be used for the diagnosis, that kind of thing. So let's go ahead to load the Bloom library and to show quickly what I mean. So I just use the tidy function and apply the tidy function on the fit model here, and here's the result. And let me make it side by side with the previous one. So the one on the top here is the result by applying the tidy function from Bloom. And the one on the bottom is the one when we just go through the summary COI and the data frame. That's the result. So right now, we no longer have those terms get restored in the row name. So we have one additional column here called named as turn here to restore those values. And also the column name here becomes more informative compared with the previous one. Right, so that's the tidy function here that extract the parameter level summary. And here, each row here would represent one parameter. And now if we want to look at, the observation level summary, you can use augment here. That would show, in addition to the column in the original data frame, where we have log2 intensity, run, and the feature, there are some additional column that are added here. So for those columns that start with the point here, that's the one came from the fit model. Say for example here, the fit column here, that would be the fit value from the model. And so the difference between the fit value, between the observation and the fit value would be the residual, etc. Right, so here, the output of the augment function would represent one observation. Now for the model level summary, we can use glance here. So it will be one row. It will be one row and with multiple columns to represent different the model model level summary for different aspects. Right, so that's the three major function of from Bloom. The tidy to extract parameter level summary, augment to extract observation level summary, and also glance to extract model level summary. Yeah, so any question for that before we move on?
Is there an easy way to combine some of the results from like the tidy and the glance together so that they're in a single data frame?
But they actually represent quite different thing, right?
So, for example,
Mhm.
the R² value and combine it with your slope intercept of the linear model.
Well, let's get both of them side by side, and we can see how we can do that. Let's say here I have so here's the return data frame of glance, and here is the output of the tidy. So they are actually for quite different level of summary, right?
Yeah. So I guess I'm curious because
Mhm.
I want to make a plot that includes the like an aggregated plot of like all of the models. So let's say I wanted to represent every single line, but using the estimate. But I also wanted kind of color coded based on the R² value, and also kind of take into account the p-value that's associated with each of things. And so they're different, you know, they're in different outputs. So I'm trying to see like how to combine them.
Yeah, I think that's exactly what the list column can help essentially. So with list column we can actually to restore the output of the tidy function, and with another column that's also a list column to restore the output of the glance function that would have the model-based summary. And if you want, you can also have a list column for essentially the observation level summary. And so that would actually to make those results or the outcome, quite essentially to restore in a quite consistent way, because now you know for every row would be some data and the model, and also the summary from the model for one particular protein, for example. Yeah. Now the remaining question would be, so how we can work with those list column, and how we can extract the information from the list column back to some format that we can easily work with. Okay, now we learn how to tidy up the object, the model object. Then we can essentially use the group by and the do method that we learned from the previous section to obtain the group summary, and then to combine with those tools. So now I would like to introduce the third approach for the first text. So we can again to use group by to define the analysis unit. So in this case, it will be protein. Yeah, because we want to get a summary for all the proteins. And so for each protein, so we'll pass on the operation through the do function, and inside the do function we'll fit the linear model, and after that we'll extract the parameter estimate with the tidy function here. So that's how you look like here. So we'll process on the train DIA2 data frame and group by based on protein here. And for each protein, we'll first to fit the linear model. And you may notice that here we have a placeholder here that would inform where the group data should go. And after that, we tidy up our LM object. So, and then we'll do the same thing as previously. We filter out. We just keep those rows that are relevant to our purpose. Those rows that contains the string of wrong here, and then to rename those essentially by removing the wrong from their name. So that's a result we can get. And essentially you can see here, so in this protein, this wrong, and that's the model-based summary, essentially the point estimate for this particular protein in this wrong, and also the associated standard error and t-statistic and the p-value. And similarly, so you get essentially similar the same result in the same format for different combination of protein and the runs.
So why is the p-value always 0?
That means it's very, very, very small. Yeah.
Is there a way to get to that to show more?
Yeah, you can do that. But I think here why the p-value is so small, because I think by using this plot it is easier to understand. Essentially, that small p-value is telling you that the wrong level, the wrong effect here is significant. That means that at different wrong, you do see the feature intensity they are at different level. So that's why the p-value is small.
Sorry, I'm just having a hard time wrapping my head around the do
Yep.
tidy LM, that section of the code. What exactly that is? Can you run through that one more time?
Okay, this part?
Yeah.
Yeah, so this part is just say with the group data or based on proteins, and then I'm going to pass on those data to the LM function here, and with the same modeling configuration that we did with the wrong and the feature as a fixed effect, and after that we tidy up the model object to extract the model the parameter level summaries. That would be, if you go back here, that would be this part.
Okay.
Yeah.
So the do is just telling you to use the previous one in that argument. The previous type in that argument. The do function.
The do function.
Is just telling you to use.
Yeah. So that's a way to allow you to perform or to perform some more arbitrary operation, because in the previous section we talked about if we want to do the summary. So you want to do the summarize, they are indeed some limitation. You can also use the summary function that would return one single value. Yeah. Right. So we actually have some discussion about if we assign a value inside the do here, that's going to create a new list column. And to show you what I mean here, so again we group by based on protein here, and we call the LM function here, and we save the result of the model into a new column, which is named as fit here. So how does this output look like? So essentially, for every protein here, so we get the output from the LM. And the Bloom package is actually, well, designed to work nicely with this type of representation. So for example, for this fit DIA data frame, and you can pass on to the tidy function and indicating that where you restore the model object. Then that would show essentially all the parameter level summary for each proteins here. And similarly, you can do the same. You can do something similar for the observation summary by using augment function. Yeah, that's going to take a while because we have that will apply for all the measurement in this data set. Yeah.
How large the data set that you can process the reasonable time within half an hour? Well, if it's too large, it will be very slow.
Yeah, that's actually one issue. So it's actually the data set we're working on is actually not very large. Yeah.
So if I have larger, what should I do?
Uh,
So how many proteins or features I can have? Usually, we will recommend in the table.
well, that depends. So first of all, that depends on how much memory you will need to restore your data frame. And then the next question will be, so what type of operation you are using to process your data, right?
So for this table, how many features?
For this one,
Yeah.
let's see. So for this one, between DIA, 33 protein, and yeah, that's we want to get a unique set of the protein and the feature, and let's count number of feature per proteins, and let's arrange. Yeah, so you may have a protein with the 32 features, and I mean that's the largest number of features in this data set. Yeah. Right, and similarly, you can get the model level summary. So that would be one row for one protein here. Right. So as we discussed, this column they can keep together those related items in the data frame, and that would essentially allow us to perform the operation in a structurally informative way. But to work efficiently with the list column, we need to we need to know those techniques that can work with lists, including those methods that can inspect the content, the element in the list, and also to compute the function, the compute with function that are developed to work with the list, and also to have a way to essentially simplify back to the original data frame, right? Because in the list column still it's not. It's a good way to put together all the related items, but in the end, you still want to transform back to a format that you can summarize your result more in a more informative way. Yeah, this way. And we are going to use the nested data frame as one example to discuss this technique. So let me go ahead to generate this nested column thing. So we can use the nest function from Tidyverse package to create a nest data frame. So what I'm doing here is for the TwinDIA2 data frame, I will add the grouping information based on proteins, and then pass on to the nest function here. And by doing so, it's going to you create a table with two columns here. The first column will contain our grouping information, which is protein, and the second one is the second column is actually a list, and every element in that list will be the data that are related to list proteins. So to make sure that is clear, so if we look at the first element in the data column here, that will give us all those data that are related to the first protein. That would be this one. And similarly, all the data related to the second protein here that are restored here. And that's what I mean. It would be good if we can have a way to restore the data and also some related item together in one single row. Then you can, if you have a way to operate on this column, then you can get, for example, some model object, the summary from the model object, and you can place them and restore them in a more informative way, because now you know for every row that would be everything related to this particular proteins. Yeah, so that's what we want to achieve. And for list nesting, so I just show essentially a shortcut here. So you can just say, I want to do the nest, but exclude the protein column. So that would essentially to create the nested data frame based on with the grouping information defined by protein. Right. So I talk about that. So in the nested data frame, each row would form a group, and the data column here essentially store those stratified data corresponding to that proteins. And we can extract the data. Yeah, we just show that with the double bracket here. That would give us all the data correspond to the first protein here. And same thing as if you provide a two-dimensional index. And now the next question would be, since we are in this format. So how can we actually to transform back to the original format? So you can use the unnest here by providing which column you are going to unnest. So this operation would essentially to repeat the value in the normal column here multiple times, essentially the same time to the number of rows here. That would match the data from the second column. So let me run here. Yeah, so that will bring back to the original format.
I have a question about the previous approach using Chrome to collect the estimates from the group by. So when I run regressions in a for loop, usually one of the 200 regression fails and then the call for fails. And what I would prefer to have is just to save the error somewhere and for the loop to keep going. So is there any way, I just wonder what is the behavior here in this approach and how to deal with the errors more gracefully.
Yeah, so the group by and do approach is probably not very well suited for that situation. And the map function that we are going to introduce. So the map function family from the PERT package that they have some additional variant from the map function that can actually handle the situation where you have the arrow and even warning message.
Okay.
Yeah. So yeah. Right. So the next thing we want to talk about is actually just the per package here. That essentially provide a set of the map function to iterate over this column and with some consistent syntax that make it easy to operate on those columns. Yeah, so the basic syntax here, the function is called map, and that would, with this, that would essentially to loop over a vector of a list called x, and applying some function here, fun, to each element of the x, and then save the result as a list. So for those of you who are familiar with lapply, so that's essentially lapply. So you will take a list or the vector as an input and operate with some function and restore as a list. And yeah, but they are, for those methods from the per package, there are some advantage. So the first one would be, so when you want to define some anonymous function, for example, here you want to define some function quickly, so it's quite handy for that. And also, if you know already that the output, the return value of the function, you know their type specifically. So you may want to provide the somehow type stable function. For example, if you know the returned value will be a double, then you can use the map underscore dbl or for other type of the variable. And in that sense, if something gets wrong, then you'll get informed immediately. Then you'll get the error message right away, rather than to restore in some way and you are not aware of that. Right, so let's first go ahead to work with this nested DIA data. So this is nested data frame that we just create. And the next thing I want to do is I want to use the mutate function and to add one more column, which is called fit. And in the fit column, that will be the output of this map function. Essentially, we apply the linear model on the data on the data column, essentially iterate over the data column here. Yeah.
So is map a lot different than Python, or can you define those differences? Because maybe I just don't understand Python very well, but yeah.
Right. So for piping is let me go back to what we have here. So that's the piping. So piping essentially is just a different way to represent this operation. Yeah, so they will do the same thing. So the piping here just means I want to operate a function here on this X object. But the map here
It applies the
what did
function-
you say?
It applies the function over a list instead of just the one variable. That's what.
you can have multiple. Essentially, the map, what the map does is to apply the function on every element in that list.
So it's like an iterative pipe.
Hmm?
Sorry. I think it's
No,
an
no.
iterative pipe. Is
Yeah,
that
right,
right?
or to use a for loop and a pipe, achieve the same. Yeah, or if you use L and Y. Right, like if you were to,
What
if you
did
were
you
to take, so if you were to use a pipe to apply a function, and you were to use a for loop to loop through the list, you would achieve the same sort of thing as you do with
Mm-hmm.
That was the question. Is that true? Thank you.
Okay. Okay, so let me first run this part quickly. So essentially, this part we are adding one column here called fit, and for every element in this list, in this list column, that's essentially we perform this LM modeling on the data here on the corresponding element in the data column. So this one will correspond to the data on the first row, etc. And you see in this map code, the first place would be the data, the object that we want to operate on. And the second place here would be the function that we define. So by doing so, yeah, so that just create one additional column to restore the model object. And once we are done with that, then we can actually to extract different level of summary as we just discussed. For example, you can use the mutate to create one additional column called parent to restore the parameter by applying the tidy function from Bloom on this model object. Now you get one more list column here, and in this list column, that essentially restore the extracted parameter estimate from this model. Right, and here is just to show you if you want to use apply, then you can achieve essentially get the same result here. And what's restored here in the new list column here? So that would essentially be, again, to be the same result as we did for one proteins. So that would be the parameter summary for one particular protein. So in this case, would be the first protein here. And of course, with the fit model, then you can do a few more things. For example, you can get the estimate for the standard deviation for the sigma here, and you know already that the sigma should be a numerical value. So you can be more specific when you call the map function. Then you want to make sure it returns a variable which is double here. Yeah, so that's a new column that we get. And if we want to get back to the original format with those parameters, then you can just specify which column that you want to carry on the nest operation. Then that would bring you back to essentially that you'll get the information from the parameter estimate and to put into a data frame and with their corresponding protein that are placed in the right place. Right, so before we move on, any question for the nested data frame and also with the map function?
So if you wanted to unnest like the program and another one, could you just add a sentence?
Which one? You
Maybe data, if you wanted to unnest like data and program.
You won't be able to do that.
Okay.
Yeah. Right. Because they are.
Right,
Yeah.
Totally.
Yeah. By just looking at the number of rows, then you know you can do that. Yeah.
What indicates that data is nested? Like, other than it, is there a way to check to see if it's nested?
It's nested data frame.
But like, so if you just see the data frame, how do you know that something is nested?
STR. So it has a list at the top.
And so that lists all.
No, I think if you have a list here, then well, one thing you can be sure would be so this column is a list column, and the way the nested data frame was created was essentially through the group by operation. That means essentially everything here should correspond to one particular protein. And say, for example, if now we get a data frame with two columns. The first one is protein. The second one is a data again. And so one thing to think about would be if you look at the unique set in the first column. So everything in the first column should be unique. If you think about the way we create the nested data frame by here, we first do a group by and then do a nest. Yeah, here. So by doing so, that would already assure that the element in the second column should correspond to the, the unique variable in the first column. So what I mean is here in the protein column, because we create the nested data frame based on this grouping information. So everything here should be unique. So this one should contain 33 proteins here as indicated here. Right, if you are getting, for example, 30 or the 20 unique protein here, that means you have some duplicate here. So that's probably not how we generate the nested data frame. And the idea to have the nested data frame is actually because we want to make sure for those data, those model object and parameter, they are associated with a single group. And if you have multiple rows correspond to that group, then, well, that may not be very useful. Any further question on nested data frame?
So I'm having trouble figuring out how to access the data that is now in this nested data frame without unnesting it. Like how to essentially
Assess the data.
the data itself.
So how would you assess the data in the list? Is that the double bracket?
Yeah.
Yeah, that would be the same.
Okay.
So, for example, now in the nested DIA here, let's say we want to access this one. So that's the third element in the data column.
Okay.
Yeah, so you will
So
just,
that will just give you that entire table. You can
Huh?
dive down deeper into data.
right. So that's just the third element here. Okay. So right. So let's talk about the last approach for the text one. So now we know how to create a nested data frame and how to operate on the nested data frame. So for text one, we can first to create a nested data frame using a group by and the nest function here. And with the nested data frame, then we can fit a linear model for each protein with list and also the map function. And we can extract the estimate from the model by using the tidy function from the Bloom package, and again with the map function. And we can use the onNest function to transform back to the original form. So let's see how it works. So the first step, we'll create a nested data frame, group by protein and nest. And after that, with this nested data frame, we'll for this nested data frame, we'll use the mutate function essentially to apply the LM modeling on every element in the data column, and then to save the result in another list column that's called fit here. So you have one column called fit, and then you essentially you apply another mutate function here through the map function here. So you apply the tidy function on your fitted model object, and then to restore the result in a column called param. So all the information related to the parameter level summary will be restored here in this list column. And after that, in the end, we want to get the run level summary. So that's restored in this column. So we want to do the unnest with respect to this column here. That would bring us back to this form. And essentially, for example, in the first row here, that corresponds to the point estimate of these proteins in run 001 here. So few additional things we need to do will be, we'll do the filter as we did before to collect those rows which are correspond to the run effect, and then to remove the run from the value here. Yeah, so that would be the output of the run level summarization using LM with this approach. Questions? Or any confusions? Okay. Right, and if you have, if you want to map over multiple vector or list, then you can use a map to map the function over 2 input vector. Or if you have more, then you can use the pmap here. So here I just show you one example. Say for example, if we have a fit model, and if we have some additional data here, so we can use the predict function to make a prediction, essentially on the data, essentially based on the model on the data you provide. So you can use this technique to make another column which is called predict. So that would essentially be the predictive value on the data that you provide using the fit model here. Right, and similarly, you can just wrap up your input to the predict function through a list, and then call the pmap function here. That will give you same result. All right, now let's talk about how we can use the approach that we've learned so far to perform the hypothesis testing to find differentially abundant proteins. Okay, so here, again, we'll first get the run level summary as what we discussed. So, as you can see here, so the run DIA here has 3 columns. First one is essentially restore the log2 intensity for every protein in every single runs. Now we want to see whether or not some protein they change in different conditions. And here we'll just look at the association between the intensity level to the zygosity. So, but before that, we need to first to bring back the sample annotation to this data frame. Essentially, we need to know what group this run belongs to. So we'll get a design matrix, essentially to first do the select. We want to select everything from the column rungs to the column visit here, and then we select those columns. And get the unique set of the rows. So that would be essentially the design matrix, the design data frame. So in this new data frame, we have 232 rows that essentially represent the 232 rungs we have. And in addition to the rung column, now we can see the annotation from all the other columns, the peer, zygosity, subject, and the type of the visit. Now we have the design column here, so the next thing we want to do would be we want to left join this design column to the rung DIA that we just get. So now in this rung DIA2 table, we have, in addition to the protein rung and log2 intensity, now we are adding the information for the sample annotation. And the next thing I want to do, again, I want to create a nested data frame based on proteins, because we want to see which protein they are differentially abundant between conditions. So we'll first create a nested data frame by proteins. And for each protein, we'll do a t-test. And to looking at the association of the log2 intensity to the zygosity here. And after that, I'll create one additional column to restore the summary of the test. Right, so that's going to have something like this. So we have the data here, we have the object from the t-test, and also the model-based summary restored in the last column. And now we have the summary for the hypothesis testing here in the last column. So we'll do an unnest with respect to the test on column. So that would, as you will see here, for every protein, though, you have the estimate for the difference between group 1 and group 2, t-statistic, p-value, etc. And so we can, again, use the select function to get those columns that are informative for us. So I'll select the protein, estimate, statistic, p-value, etc. and save it in the div ZYG data frame. So let's take a look at this output. So here you show for every single protein what's the estimate for the difference, and the t-statistic and the p-value, and the lower bound and higher bound of the confidence interval for the difference estimate.
So the t-test is based on the intensity of all the runs, right?
Based on the intensity of all runs belong to one group versus the other.
Yeah.
And
what if there's one run that goes bad? Is there a way to filter it out? How do you decide which ones to use and which ones bad?
sometimes, for example, in my spot, that how do you rule out something that
I think those issues related to the quality control should be, should be addressed upfront. So you shouldn't choose those values to do the statistical testing at this phase, because that would otherwise like you are essentially choosing those measurements that make more sense to you. Yeah.
I think that there's a lot of error handling functions. You can try or try catch, just like Python. So you can continue running over the loop as well as you can give it good breaks down so you can do error handling.
Those are slightly different things. The error handling, of course, is if you, that was kind of addressed the question that was asked earlier about how you can continue running something when you run into an error. I heard someone ask that earlier, and there's a couple functions called try and try catch that you can use that will continue running things. You'd have to decide precisely where to put it, of course. For this question, the question was more about quality control, and so that would be something that you would probably want to, when you're first exploring your data, you're first plotting all the original things that Tsung-Heng plotted at the beginning of everything. That's when you would notice, oh, this run is bad, I probably want to filter it out, and then you can just use the filter functions that you showed to do that.
Okay. Very last step. So yesterday, someone pointed out, okay, when we are doing the testing for all the proteins, so we should consider the multiple testing correction. So here we have a list of p-value. So we can use the p-adjust function to essentially to get the adjust p-value. And here we'll use the Benjamin and Holberg method. And so we'll use the mutate to create, essentially to add one variable to restore the adjusted p-value. And again, it's always used for once we get down to this level of summary, so it would be good to order your summary based on your adjusted p-value. And then here you will know, okay, for this particular protein, it has the lowest adjusted p-value, and also you can also look for some other estimate. And that will be the way to essentially to create starting from creating the workflow and getting the summary at different level and transforming back to a data format that makes sense to people and to get some insight for follow up. Yeah, so that's probably all for this section. So, any question before we wrap up?
Could you maybe explain what all the columns mean again?
Oh, the color.
The estimate and the t-statistics, what is exactly?
Okay, so the estimate here would be the estimate of the difference.
It's a changes of the log.
Yeah, so here we are, because we are using the log2 intensity as an input. So by doing t-test, you are essentially comparing the average value between two groups. And here it will be the average value of log2 intensity in one group versus the other. And the estimate here will be, because we are doing t-test, so that would be the difference between the average of log2 intensity in one group versus the other. So that will be the first column. And the second one will be the t-statistic. So the t-statistic will be the difference divided by the standard error of that estimate. Right. So there will be one standard error correspond to this difference estimate, and the ratio will be the t-statistic. And a p-value is from you use the t statistic and to compare against a reference distribution for the t-test, then you get a p-value. Confidence interval, yeah. So that's similar concept. So essentially, when you do the modeling, so you have a way to get a point estimate as well as the uncertainty estimate for the point estimate. Then you can, yeah. So by some math, then you can get both bound of the confidence interval.